Hi, and welcome to day 27 of Just Start Programming, the Rust programming language. The other day we started on one of the most interesting topic in Rust, which is fearless concurrency. Today let's continue and touch on how messages can be passed or transferred to another threads. It's an advanced topic, so let's take it slow, sit back, and relax. Join me learning it live in one take. No shortcuts, no secrets. So let's just start programming. Okay, so the other day we tried using threads to run code simultaneously. So let's just have a quick review. Let's glance through the topic before we proceed with using message passing to transfer data between threads. So this is just to refresh our memory. Okay, using threads. The features that run these independent parts are called threads. And then because they can run simultaneously, there's no inherent guarantee about the order in which parts of your code on different threads will run. This can lead to problems such as race conditions, in which threads are accessing data or resources in an inconsistent order, deadlocks, in which two threads are waiting for each other, preventing both threads from continuing, bugs that happen only in certain situations and hard to reproduce and fix reliably. Okay, here Rust attempts to mitigate the negative effects of using threads, but programming in multi-threaded contexts still takes careful thought and requires code structure that is different from that in programs running in single thread. So all this time we have been programming only in single thread. But now uh, we are introduced to this multi-threaded programming. So how do we create new thread? Creating new thread with spawn. So this is how it looks. Thread spawn. Let's take a look at the example. So main thread, and then it will spawn 1 to 10 threads. So thread will sleep for this duration, which is I think this is 1 millisecond. So this one will create 10 threads. And then this one will create 5 threads. Okay. The output will look like this. Hi, number 1 from main thread. Spawn thread. Okay, so this is the spawn thread. Spawn. While this is main thread. Okay, so you have main thread. The main thread is not spawning anything, so it's just running on its own. But there's a sleep. Although this will increment from 1 to 5, but this one is still just one thread. While as over here, this will spawn a separate thread. So you have 1 to 10. But what we can see here in the output, spawn thread reached 5. Yeah. Why is it that we only have 5? We have 10 here. Okay. So here's the explanation. Even though we told the spawn thread to print until I is 9, it only got to 5 before the main thread shut down. Because at this point, by having the main thread only count from 1 to 5, when it reaches 5, the main thread already shut down, so it cannot spawn additional threads. That's the explanation here. If you run this code and only see output from the main thread, or don't see any overlap, try increasing the number in the ranges to create more opportunities for the operating system to switch between threads. Yeah, so both of them are having the same duration, so it's almost, they will almost have the same number, like this one. I think last time when we were running this, over here, 1, 2, 3 to 9. Oh, so a spawn thread got to 9. Why is that? I think this one, because we did something like this where the threads are joined together. Yeah. So if we comment out this one, and this one is commented out, so this one will spawn basing on this range. Let's see if it reaches 10. Yeah, so the spawn thread got to 9. Main thread was able to count 1, 2, 3, 4. Or it didn't have 5. By 5, the spawn thread got to 9. So the join waits for the associated thread to finish. This function will return immediately if the associated thread has already finished. Okay, so that's how you join threads. Yeah, waiting for all threads to finish using join handles. Okay, so but which one will have the handle? Handle, okay, the one with the handle is actually the one with the spawn. So it will wait for this to reach, okay, the range is from 1 to 10. Essentially, that's having 9. Is it 9? 1, and then 10. I think it should be 10. It will wait for its thread to finish. Okay. When we call the join method on it, we'll wait for its thread to finish. Join. So it will wait for this thread to finish. Okay, so here in listing 16-1, Listing 16-2 shows how to use join handle of the thread created in listing 16-1 and how to call join to make sure the spawn thread finishes before main exits. So it ensures that spawn thread finishes before the main thread, this one, within this scope, will exit. Okay, calling join on the handle blocks the thread currently running until thread presented by handle terminates. Blocking a thread means that the thread is prevented from performing work or existing. Because we put the call to join after the main thread's for loop running in 16-2 should produce similar outputs. Yeah. Two threads continue alternating, but the main thread waits because of the call to handle join. It does not end until the spawn thread finishes. So spawn will just return handle. It does not end until the spawn thread is finished. Okay, but in this case, if you put it here, the main thread will wait for the spawn thread to finish and then run its for loop. So the output won't be interleaved anymore, as shown here. So this one will still continue, but this one will be executing first and then it will wait. And then 1 to 5 here will run. So you see this order here. To 5, so that is 1 to 4 from here, 1 to 4. Small details such as where join is called can affect whether or not your threads run at the same time. I'm not sure if we did this part using move closures with threads. Let me just check. Okay, so yeah, so let's start with this. Okay, using move closures with threads. You'll often use the move keyword with closures passed to thread spawn, because the closure will then take ownership of the values it uses from the environment, thus transferring ownership of those values from one thread to another. In capturing environment with closures, chapter 13, closures. What did we have here? This part, the one with the pipe, closure type inference and annotation. Yeah, this one. So it looks similar to functions. Okay, let's go back. We discussed move in the context of closures. Now we'll concentrate more on the interaction between move and thread spawn. Notice in listing 16-1, the closure we pass to thread spawn takes no arguments. Oh, where is it? This one. So it's a closure. It doesn't contain any environment value. Arguments. Sorry, not environment, but arguments. We're not using any data from the main thread in the spawn thread's code. To use data from the main thread in the spawn thread's closure must capture the value it needs. Listing 16-3 shows an attempt to create a vector in the main thread and use it in the spawn thread. However, this won't work yet, as you'll see in a moment. Okay, that's what we have here. We have a vector, and then one thread will be spawned, and then print. Here's a vector. How are we passing the vector? Okay, so it says it will not work yet. The closure uses V, so it will capture V and make it part of the closure's environment. Because thread spawn runs this closure in a new thread, we should be able to access V inside that new thread. But when we compile this example, we get the following error. Okay, closure may outlive the current function, but it borrows V, which is owned by the current function. May outlive borrow V. Okay. To force closure to take ownership of V and any other reference variable, use the move keyword. Oh, so it's suggested here, move. Okay, let's see. Rust infers how to capture V, and because println only needs a reference to V, the closure tries to borrow V. However, there's a problem. Rust can't tell how long the spawn thread will run, so it doesn't know where the reference to V will always be valid. Whether the reference to V will always be valid. 16-4 provides a scenario that's more likely to have a reference to V that won't be valid. Okay, reference to V that won't be valid. Okay, so here drop V. Yeah, so drop V is in the main thread, and then within this thread, of course, we wouldn't know if V would still be valid. Okay, if Rust allowed us to run this code, there's a possibility that the spawn thread would be immediately put in the background without running at all. Spawn thread has a reference to V inside, but the main thread immediately drops V, using the drop function we discussed in chapter 15. Then when the spawn thread starts to execute V is no longer valid. So a reference to it is also invalid. Oh no. To fix a compiler error in listing 16-3, you can use the error message advice. So there's a move here. By adding move keyword before the closure, we force the closure to take ownership of the values it's using rather than allowing Rust to infer that it should borrow the values. The modification to listing 16-3 shown in listing 16-5 will compile and run as we intended. So the only difference is we have move here. So we are forcing the closure to take ownership of the values. It's using rather than allowing Rust to infer that it should borrow the values. Okay, so this is an interesting example. Let's put it here. out. This one doesn't have any violation error. Here's a vector. Okay, so that one worked. We might be tempted to try the same thing to fix the code in 16-4, where the main thread called drop by using a move closure. However, this fix will not work because what listing 16-4 is trying to do is disallowed for a different reason. If we added move to the closure, we would move V into this closure's environment, and we could no longer call drop on the main thread. We would get this compiler error instead. Okay, so I think drop was added after this one. So let's do a drop. V. So this one will have an error. Okay. Rust ownership rules have saved us again. We got an error from the code in 16-3 because Rust was being conservative and only borrowing V for the thread, which meant the main thread could theoretically invalidate the spawn thread's reference. Yeah, so this is the reason. Theoretically. And then by forcefully dropping it, of course, this is a clear example. It was dropped, and there's no way the spawn thread will have a reference to that one. 16-4. Okay, I think this is the one with a drop. Okay, the move keyword overrides Rust conservative default of borrowing. It doesn't let us violate the ownership rules. Now that we have covered what threads are and the methods supplied by the Thread API, let's look at some situations in which we can use threads. Okay. All right, so here we are using message passing to transfer data between threads. One increasingly popular approach to ensuring safe concurrency is message passing, where threads or actors communicate by sending each other messages containing data. Here's the idea in a slogan from the Go language documentation. Do not communicate by sharing memory. Instead, share memory by communicating. Do not communicate by sharing memory. Instead, share memory by communicating. What exactly does it mean? To accomplish message sending concurrency, Rust standard library provides an implementation of channel. A channel is a general programming concept by which data is sent from one thread to another. So message passing through a channel. Okay. You can imagine a channel in programming as being like a directional channel of water, such a stream or a river. If you put something like a rubber duck into a river, it will travel downstream to the end of this waterway. So, yeah, so it's not a TV channel, but a channel of water traveling downstream. A channel has two halves, a transmitter and a receiver. The transmitter half is the upstream location where you put the rubber duck into the river. The receiver half is where the rubber duck ends up downstream. So downstream is the receiver half. One part of your code calls methods on the transmitter with the data you want to send, and another part checks the receiving end for arriving messages. A channel is said to be closed if either the transmitter or receiver half is dropped. Okay. Stream of water, channel of water flowing down. It is closed if either the transmitter or receiver is dropped. Here we'll work up to a program that has one thread to generate values and send them down a channel, and another thread that will receive the values and print them out. We'll be sending simple values between threads using a channel to illustrate the feature. Once you're familiar with the technique, you can use channels for any threads that need to communicate with each other, such as a chat system or system where many threads perform parts of calculation and send the parts to one thread that aggregates the results. First, in listing 16-6, we'll create a channel but not do anything with it. Note that this won't compile yet because Rust can't tell what type of values you want to send over in the channel. This is MPSC. Let TX, RX. This one looks like a tuple. So MPSC channel. Okay. Creating a channel and assigning two halves to TX and RX. We create a new channel using MPSC channel. Function MPSC stands for multiple producer, single consumer. MPSC, multiple producer, single consumer. Okay. In short, the way Rust standard library implements channels means a channel can have multiple sending ends that produce values, but only one receiving end that consumes those values. Imagine multiple streams flowing together into one big river. Everything sent down any of the streams will end up in one river at the end. We'll start with a single producer for now, but we'll add multiple producers when we get this example working. Okay. MPSC channel functions return a tuple, the first element of which is the sending end, the transmitter, and the second element of which is the receiving end, the receiver. The abbreviations TX and RX, okay, so transmitter, receiver, are traditionally used in many fields for transmitter and receiver, respectively, so we name our variables as such to indicate each end. In communication, so transmit and receive. We are using a let statement with a pattern that destructures the tuples. We'll discuss the use of patterns in let statements and destructuring in chapter 19. For now, know that using a let statement this way is a convenient approach to extract the pieces of the tuple returned by MPSC channel. So like this. Let's move the transmitting end to the spawn thread and have it send one string so the spawn thread is communicating with the main thread, as shown in 16-7. This is like putting a rubber duck in the river upstream or sending a chat message from one thread to another. Okay. Let's copy this one. this part. Let's put that over here. TD time duration. Where's that coming from? Oh, okay. Let's remove use MPSC. We don't need that one. Like this. Set like that. Oh, STD thread. Just STD thread. It's already there at the top. Okay. Yeah, I accidentally commented out some of the libraries. That is fine. Anyway, we have commented out duration. Yeah. Okay, so what we have here, TX, RX from MPSC channel. So there's a thread that is spawned here. Okay, there's a string high value, so TX will send val and then unwrap. Okay, what does it do? Maybe let's run it first and see. Fearless Concurrency. That's our project. Okay, I cannot see any output from here. And let's read the explanation. So we're using thread spawn to create a new thread, and then using move to move tx into closure. Oh, this one, we need to move it into the closure. So the spawn thread owns tx. So the spawn thread now owns tx. The spawn thread needs to own the transmitter to be able to send messages through the channel. Transmitter has a send method that takes the value we want to send. The send method returns a result type. Okay, result type. Then we have unwrap. So if the receiver has already been dropped and there's nowhere to send the value, send operation will return an error. In this example, we're calling unwrap to panic in case of an error. But in real application, we should handle it properly. Return to chapter 9 to review strategies in proper error handling. Okay, but for now, unwrap can be used. 16-8 will get the value from the receiver in the main thread. This is like retrieving the rubber duck from the water at the end of the river or receiving a chat message. Okay, so this one will send hi. Let me have receive. Okay, RX, the receiver, receive, unwrap. it will be stored to receive. So this one got should be high. Okay, let's try that one out. So it means the main thread printout got high. Let's run it. Okay, got high. So it was received from the spawn thread to the main thread. Okay, the receiver has two useful methods, receive and try receive. Okay, receive is here. We're using receive, short for receive, which will block the main thread's execution and wait until the value is sent down the channel. Okay, so it will block. Once the value is sent, receive will return result. When the transmitter closes, receive will return an error to signal that no more values will be coming. Try receive method doesn't block, but will instead return result immediately. An OK value holding a message if one is available, and an error value if there aren't any message this time. Using try receive is useful if this thread has other work to do, waiting for messages. You could write a loop that calls try receive every so often, handles a message if one is available, and otherwise does other work for a little while until checking again. Okay. So receive will block, try receive will not block. So it will run. And then immediately an OK value holding the message if one is available, and ERR value if there aren't any message this time. We've used receive in the example for simplicity. We don't have any other work on the main thread to do other than wait for messages. So blocking the main thread is appropriate. When we run the code, 16-8, we'll see the value printed from the main thread. Okay, I think we've seen that in the code also. Let's run it again. Got high. Okay, channels and ownership transference. The ownership rules play a vital role in the message. Wait, let me just check again. Receive got receive. Okay, I'm just looking at these two. Send is here and receive is here. I'm just thinking if we have multiple threads, then the receive will have multiple values depending on the thread. Okay, channels and ownership transference. The ownership rules play a vital role in message sending because they help you write safe concurrent code. Preventing errors in concurrent programming is the advantage of thinking about ownership throughout your RAS programs. Let's do an experiment to show how channels and ownership work together to prevent problems. We'll try to use a value in a spawn thread after we've sent it down to the channel. Try compiling the code listing in 16-9 to see why this code isn't allowed. Okay, let's do some analysis also. Okay, the same as last time. We have transmit and receive. Here you have move. So if you use tx, you can use it. But you have val here. Wrap. Receive rx. Receive unwrap. Print line got received. Why it won't compile? Is it because of this? Why is this different from this one? We also have val here. Then move. Send to val. Send val. Send val. We have this one. So this one will work. Is it because of this one? Let's see. Here we try here we try to print val after we send it down the channel by tx send. Okay, allowing this would be a bad idea. Once the value has been sent to another thread, that thread could modify or drop it before we try to use the value again. Potentially, the other thread's modification could cause errors or unexpected results due to inconsistent or non-existent data. However, Rust gives us an error if we try to compile the code in 16-9. Okay, this is the culprit. Here. That's it. There. Okay. Our concurrency mistake has caused a compile time error. The send function takes ownership of its parameter, and when the value is moved, the receiver takes ownership of it. This stops. Okay, receiver takes ownership of it once it is moved. This stops us from accidentally using the value again after sending it. Ownership system checks that everything is okay. Okay, I think this is the one that I wanted to do. Sending multiple values and seeing the receiver waiting. Okay. The code in 16-8 compiled and run, but it didn't clearly show us two separate threads. Okay, let me comment out this one first because it is illegal. Cannot do that. So by using move, the spawn thread takes ownership of this value. What do we have here? You can copy this and comment out this one. This one. Oh, maybe let's just copy that one instead. But here, Okay, duration. Okay, so this one will just add the import. So it should be up there. Duration. Okay, so let's run this one. Got hi, got from. Okay. Is there a delay? Yeah. So there's a sleep. While spawning, you have a vector containing string elements hi from the thread. Okay, then from here, it will send it and sleep for 1 second. And then at the receiving end, Rx string in Rx receive contains string. Okay, got receive. This is a nice illustration of a demo of threading, because you can see once it received something, then this one will display. So this part here is still running in the main thread, while this one is already spawning separate one. Okay. This time the spawn thread has a vector of strings that we want to send to the main thread. We iterate over them, sending each individually, and pause between each by calling the thread sleep function with a duration value of 1 second. Yeah. In the main thread, we're not calling the receive function explicitly anymore. Oh yeah, it's just a for loop. You have Rx here. Anything inside Rx will print this one immediately. Ah, nice. For each value received, we are printing it. When the channel is closed, iteration will end. Somehow it looks something like when you ask, okay, let's okay, for example, we are searching for a halting problem. If we search this, maybe let's make it more complex. Halting problem in Rust sample code. Yeah, so it's generating. I think it behaves something similar to transmit and receive. So the AI is transmitting, and then in the browser it's receiving the message from the AI. Something like that. Okay. Yeah. So here you can see hi from the thread. So it's being sent, and then it shows up once it is received. Hi from the thread. Okay. This for loop here, does it constantly loop? or it only prints if it receives something. Okay. Let's see that I wanted to do. Okay, so for example, I wanted to know what's the difference between this for loop and the typical loop that we have for x in 1, 2, 10. Can I do something like this? One. I think this one got is in another loop. What do you think will show up? Okay, so loop 1 already finished, but this one is still running. In Rx. This behavior is a bit strange. Does it mean that it's not looping continuously, but as you receive something, it will display it here? Okay, so let's just assume that it's only executing this part if it receives something. It's unlike this one where you already have the range. So the range, it means that it will execute line by line from, okay, the range is 9. 10 minus 1, so 9. Okay, so that's interesting. Yeah, using for loop to receive something here. Okay, let's continue. Following output with a 1-second pause. Yeah, 1-second pause. That is mainly from the sender, actually. Send sleep 1 second. Yeah, but if you make this smaller, of course, it will receive the message much more faster. So let's try. Can we put 0.5? It work. U64 mismatch. Incorrect. And we will not use that. Maybe 30. From millisecond 30. So it should be running much faster. Sending, okay, there. That was fast. I might have seen something. F32, so there's a floating point. So it means this one we can put 0.5. Hmm. Yeah, so that's half a second. So it depends on the sender. Okay. Creating multiple producers by cloning the transmitter. Okay. Earlier we mentioned that MPSC was an acronym for Multiple Producer Single Consumer. Let's put MPSC to use and expand the code in listing 16-10 to create multiple threads that all send values to the same receiver. You can do so by cloning the transmitter as shown. Still have a vector, but where's the clone? Clone? Oh, here. tx1 is equals to tx clone. So we're cloning the transmitter. Okay, tx1. But where is this thread spawn? Oh, this is tx1. tx1 sends the value unwrap. So since we are using val here, we need to have move thread slip. So it will slip for 1 second. And then here, thread spawn move. Okay. It's another one. String messages for val in val. Send which one? Val. Tx clone. This one. Okay, so this one is the main thread. Tx. No, this is tx. This is for tx. This is for tx1. Okay. Receive. Not receive. Let's see. Copy this one. Put it here. This one we can get out. So how will it look like? So it depends on who is sending it. Much faster. I think there will be some overlap. Okay, let's see. Hi, more from messages. The 4 thread U. Who is having hi? Hi is from tx1. More is in tx. From. Let's switch back to tx1. Messages. Which one has messages? Messages is in original. Then the. I think it's referring to this one. 4. It does this one. Then thread. And then U. Okay. Hi, more. From messages. The 4. Thread U. Okay. That's the order that it was executing. Okay, so having multiple threads sending to same channel. Dx. Oh, wait. I think there's more to this. Because here, okay, we're doing a clone dx1. Dx1 is here. How does it know that Rx? Okay. Is it because of Rx MPSC channel Tx is being cloned? So Tx1 will also have it. That's interesting. Let's see the explanation. This time, before we create the first spawn thread, we call clone on the transmitter. This will give us a new transmitter we can pass to the first spawn thread. We pass the original transmitter to a second spawn thread. This gives us two threads, each sending different messages to the one receiver. You might see the values in another order. Okay, so it's also possible they won't be in the same order. Depending on your system, this is what makes concurrency interesting as well as difficult. If you experiment with thread sleep, giving it various values in different threads, each run will be more non-deterministic and create different output each time. Now we've looked at how channels work. Let's look at a different method of concurrency. Okay, maybe we go back to the statement. Do not communicate by sharing memory. Instead, share memory by communicating. Okay. Message passing, where threads or actors communicate by sending each other messages containing data. So that is already the transmit receive. Do not communicate by sharing memory. Instead, share memory by communicating. I still don't have any clue. I don't know Go language as well. Data races cannot occur by design. Okay, only one Go routine has access to a value at a given time. To encourage this way of thinking, we have reduced it to a slogan: do not communicate by sharing. This approach can be taken too far. Reference counts may be best done by putting a... Oh, there's also reference counts here. Okay. Easier to write correct programs. Where were we? Programming. Oh, no. The disclosures. Okay. So let's come back here. So this is one way of passing value. There's a closure. You have the move keyword. You're making the thread as the owner of the variable. So you cannot use the val somewhere else. Mm. Cannot use the val somewhere else. Okay, but you can receive the value using the receiver, and you can have like a for loop here. Okay, so since this one is only one thread having, it's like streaming these messages, because of the for loop, takes it one by one with a delay of 1 second. Then you can see that in the once it receives something, the first second high, then it will receive high, then it's not receiving anything, and the next second it's from, and it receives from. Okay. Another approach at, so here let's look at a different method of concurrency. This is, now you have shared state concurrency. Message passing is a fine way to handle concurrency, but it's not the only way. Another method would be for multiple threads to access the same shared data. Consider this part of the slogan from Go language documentation. Do not communicate by sharing memory. What would communicating by sharing memory look like? Communicating by sharing memory. In addition, why would message passing enthusiasts caution not to use memory sharing? In a way, channels in any programming language are similar to single ownership. Because once you transfer a value down a channel, you should no longer use that value. Shared memory concurrency is like multiple ownership. Multiple threads can access the same memory location at the same time. As you saw in chapter 15, where smart pointers made multiple ownership possible. Multiple ownership can add complexity because these different owners need managing. Rust type system and ownership rules greatly assist in getting this management correct. For example, let's look at mutexes. One of the more common concurrency primitives for shared memory, mutex. Okay. Using mutex to allow access to data from one thread at a time. Okay. Mutex is an abbreviation for mutual exclusion, as in mutex allows only one thread to access some data at any given time. To access data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex lock. The lock is a data structure that is part of the mutex that keeps track of who concurrently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds via locking system. Okay, so you have mutex, then you have locking, allows only one thread to access some data at any given time. Mutexes have a reputation for being difficult to use, because you have to remember two rules. You must attempt to acquiring the lock before using the data. When you're done with the data that the mutex guards, you must unlock the data so other threads can acquire the lock. Okay, so it means you must unlock the data so other threads can acquire the lock. Yeah. So since a thread is done with the data, and when you attempt to acquire the lock for using the data, so the thread could unlock the data so other threads can acquire the lock. Okay, so these are the rules. For a real-world metaphor for a mutex, imagine a panel discussion at a conference with only one microphone. Before a panelist can speak, they have to ask or signal that they want to use a microphone. When they get the microphone, they can talk for as long as they want, and then hand the microphone to the next panelist who requests to speak. If the panelist forgets to hand the microphone off when they're finished with it, no one else is able to speak. This is a good analogy. Metaphor. If management of the shared microphone goes wrong, the panel won't work as planned. So the microphone is the lock, the mutex. Management of mutexes can be incredibly tricky to get right, which is why so many people are enthusiastic about channels. Okay. I think channels is much more easier to use. But for sure, there would be some use cases for mutexes also. However, thanks to Rust type stream and ownership rules, you can get locking and unlocking wrong. Oh, okay. So in Rust, you can get locking and unlocking wrong. Okay, is that possible? The API of mutex. As an example of how to use a mutex, let's start by using a mutex in a single-threaded context, as shown in 16-12. 16-12. Mutex main mutex new 5 m lock unwrap. Okay, so the lock is already called here. So it will return a mutable num. Okay, so it could be 5. Mutable num. Okay, and here it's dereferencing num equals to 6. Okay, maybe let's read through the explanation. As with many types, we create a mutext using associated function new. To access the data inside the mutex, we use lock method to acquire the lock. This call will block the current thread so it can't do any work until it's our turn to have the lock. The call to lock would fail if another thread holding the lock panics. In that case, no one would ever be able to get the lock. So we've chosen to unwrap and have this thread panic if we're in that situation. Call to lock would fail if another thread holding the lock panic. Okay, so it will fail if another thread holding the lock panic. So we've chosen to unwrap and have this thread panic if you're in that situation. So something panic, then so the thread will also signal panic. Okay, after we have acquired the lock, we can treat the return value named num, in this case, as a mutable reference to the data inside. Mutable reference to the data inside. The type system ensures that we acquire a lock before using the value in M. The type of M is mutex, not I32, so we must call lock to be able to use I32 value. Can't forget the type system won't let us access the inner I32 otherwise. It's a type mutex. You need to get the lock first, otherwise you cannot access num. Okay. As you might suspect, mutex is a smart pointer. More accurately, the call to lock returns a smart pointer called mutex guard wrap in lock result. We handle with a call to unwrap. The mutex guard smart pointer implements dref to point at our inner data. Oh, so it's similar to smart pointer. So you dereference it first. The smart pointer also has a drop implementation that releases the lock automatically when mutex guard goes out of scope, which happens at the end of the inner scope. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads. Because the lock release happens automatically. So there's a drop implementation when mutex guard goes out of scope. Mutex guard goes out of scope from here, which happens at the end of the inner scope. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads. Okay, because the lock release happens automatically. After dropping the lock, we can print the mutex value and see that we were able to change the inner I32 to 6. Okay, so after dropping the lock. Okay, so I think this one is still referring to this. Mutex guard goes out of scope. Okay, mutex guard goes out of scope. M. Let me copy this one. Mutex. Let me comment out these things here. First, let's try running this to see. Oh, there's an error in MPSC. Cannot infer type of parameter T. It's not needed because now we are only using mutex. Okay, let's run this one. Mutex data6 Poisson. Oh, why do we have all this displayed? Poisson false. Mutex M. Who is displaying that one? Mutex M. This one, the print line. So it was changing the value internally. So this one, dereference here, dereference mutable for mutex guard. Mutex guard. So it's extracting this one, the I32 part. What happened there? Okay. Exploring API mutex in a single threaded context for simplicity. Okay, so this is single thread. As with many types, we create mutex T using the associated function U. To access the data inside the mutex, we use lock. Okay, lock method to occur the lock. This call will block the current thread so it can't do any work until it's our turn to have the lock. So it will block. To call the lock, the call to lock would fail if another thread opening the lock panicked. In that case, no one will be able to get the lock, so we have chosen to unwrap this thread back. I think we've gone through this. Sharing mutex between multiple threads. Now let's share a value between multiple threads using mutex. We'll spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. We will have a compiler error, and we'll use that error to learn more about using mutex. How Rust helps to use it correctly. Now what's in here? Mutex thread, mutex new. Okay, this one has a mutable handle to a vector, and within this range there's a spawn of the thread. Is it for num? Most likely is for num. Push handle. Push handle. Is this something new? Is it part of the spawn? I think so. It's part of the spawn. Handle in handles. Join. Drop. Okay. So I think we'll save this for another day. I think this is quite long. Let's do some analysis on this. next day. All right, so let's end here for now. Anyway, we have seen how we can make use of a channel like a channel of water. You have the transmit, receive kind of approach for threading, multi-threading, concurrency. Yeah. Okay, let's end here for now. Thank you so much for accompanying me today, learning another topic under fearless concurrency. But before I finally end this live programming, let me thank my supporters. Thank you so much.